Welcome to the Deep Dive. We're the show that takes concepts you think you've got figured out and, well, dives deeper.
Yeah, find the hidden layers.
Exactly. And today we're tackling something huge, fundamental really, but often just the water cycle.
Right, that diagram we all drew in school. Sun, clouds, rain.
That's the one. Seems simple, maybe even too simple for a deep dive.
You'd think so, wouldn't you? But it's actually one of Earth's most powerful engines. Seriously.
Totally. It shapes weather, climate, basically all life. So our mission today is to go way beyond that classroom drawing.
We're going to look at where Earth's water even came from. Spoiler, it's kind of cosmic.
Ooh, intriguing. And then we'll unpack each stage, right? Evaporation, condensation.
Precipitation, collection,
Right.
yeah. But looking at the mechanics and stuff you don't usually hear about, the nuances.
We want to connect the tiny dance of water molecules to, global climate. Show how this ancient cycle matters right now to you.
Basically, you'll never look at a puddle the same way again.
Okay, so let's do a super quick refresh on the basics, the school stuff, then blast off to the origins. Sound good?
Let's do it.
All right, evaporation. That's step one. Heat, usually from the sun, turns liquid water, oceans, lakes, whatever, into water vapor, a gas.
Right, it rises up, then comes condensation. That warm, moist air goes up, it cools down, and the vapor turns back into tiny little water droplets or ice crystals. That's how clouds form.
Got it. Clouds get heavy, can't hold any more water, and boom, precipitation.
Rain, snow, sleet, hail, depends on the temperature and conditions up there.
And finally, collection. All that water gathers back up. Rivers, lakes, oceans, even underground.
And the whole thing starts over. Liquid, gas, solid, round and round. That's the absolute core idea.
But, okay, why does this cycle matter so much? Beyond just giving us rain.
Well, for starters, it's endless recycling. The water we have now, it's pretty much all the water Earth has ever had. Same molecules circulating for billions of years. Think about that.
Billions. Wow, okay.
And it's crucial for Earth's energy balance. Evaporation takes heat away from the surface. It cools things down.
Like sweating.
Exactly like sweating. Then, when condensation happens up in the atmosphere, it releases that stored heat. This whole exchange helps regulate the planet's temperature.
Ah, okay. And it drives all our weather, doesn't it?
Absolutely. Storms, droughts, wind patterns, climate zones, they're all fundamentally expressions of the water cycle moving energy and moisture around the globe.
It really connects everything. That idea you mentioned, water falling in a rainforest, could end up, centuries later in a desert cloud?
It could, yeah. It links ecosystems, continents, timescales in ways that are frankly profound.
It gives you that sense of wonder, too, like the water in your coffee this morning.
Could have been in a glacier, yeah.
Yeah.
Or maybe sipped by a dinosaur. Or part of a cloud over ancient Rome. It's mind-boggling.
It really is. Nature's ultimate recycler, just constantly going.
Never stop.
Which brings us to a really fascinating question. If it's a cycle, an endless loop, did it have a beginning? When did the first water cycle actually start?
Ah, that's a great question. And the answer takes us way, way back. Before Earth.
Before Earth. Okay, how?
Well, think about water, H2O, the hydrogen atoms. They were formed in the Big Bang, 13.8 billion years ago. Some of the oldest stuff in the universe.
Me, seriously? Okay, so H is ancient? What about the O, the oxygen?
That came later, forged inside massive stars through nuclear fusion. Then, when those stars exploded supernovae, they scattered that oxygen across space.
Wow. So the ingredients were made separately, billions of years apart, in completely different cosmic events.
Pretty much. And then, somewhere out in the cold darkness of interstellar clouds, those hydrogen and oxygen atoms eventually found each other, bonded, and formed water molecules, mostly as tiny ice crystals just floating in space.
So water existed before planets, just drifting.
Waiting, you could say. Waiting for a place like Earth to form.
Okay, my mind is slightly blown. So Earth forms roughly 4.5 billion years ago. It's a hot, molten mess initially, right? No oceans. How does that space water get here?
Two main ways. First, outgassing. Volcanoes on the young, cooling Earth released gases trapped inside the rock, and a lot of that was water vapor. Steam, basically.
Okay, so some came from within.
Right. But a huge amount likely came from comet and asteroid impacts. These icy bodies, formed in the outer solar system, bombarded early Earth for millions of years. Think of them as giant water deliveries from space.
Like cosmic water balloons.
Sort of, yeah. And as Earth cooled down enough, all that vapor in the atmosphere from volcanoes and impacts started to condense. and it rained.
The first rain.
The first rain, and likely not just a shower. We're talking potentially thousands, maybe millions of years of continuous planet-covering rainfall, enough to fill the ocean basins relatively quickly, geologically speaking.
Unbelievable. So those first rains filling the first oceans, that's the start of Earth's water cycle.
That's the start of the cycle on Earth, yeah.
Yeah.
Once you have liquid water on the surface in an atmosphere, the loop, evaporate, condense, precipitate can begin.
Must have been a wild scene back then.
Oh, absolutely. Imagine a planet shrouded in steam, torrential rains constantly falling, no plants, no soil, just rock and ocean under a maybe dimmer sun. A much more violent, raw version of the cycle. Simpler, maybe, but the core process was there.
So when we ask when did it begin, it's complicated.
It really is. Do you mean when H and O first formed? When they combined in space? When the first drop hit proto-Earth? Or when the loop actually started circulating here? There's no single easy answer.
It's almost philosophical.
It kind of is. Asking about the water cycle's start is like asking about the start of life or the universe. They're all tangled together. That water in your glass isn't just water, it's ancient history. Older than the ground beneath your feet.
Definitely puts that school diagram in its place.
Okay, let's zoom in now on evaporation. We said it's water turning into vapor, but there's more to it, right? Oh, much more. It's not just water drying up. It's a constant, quiet escape of molecules. Needs energy, usually the sun's heat, but wind helps too. And it happens even when it's not hot out, just slower.
And it's happening at the molecular level. The water molecules are always jiggling around.
Constantly moving, yeah. Some have more energy than others. The ones right at the surface, if they get energetic enough, they can actually break the bonds holding them to their neighbors, the hydrogen bonds, and just leap off into the air as vapor.
And that's why it cools things down. Because the fastest, hottest molecules are the ones leaving.
Exactly. The average energy of the water left behind drops. It's a natural cooling process. That's how sweating cools your body. Your sweat evaporates, taking heat with it.
So evaporation isn't just moving water, it's moving energy, heat energy.
Massively important. It's one of the planet's main ways of redistributing heat. And the rate it happens depends on things like temperature, obviously, but also humidity. If the air is already full of vapor, it's harder for more to escape.
Wind too, you said.
Yeah, wind sweeps the vapor away from the surface, making room for more evaporation. And surface area matters. A wide, shallow puddle evaporates way faster than the same amount of water in a tall, narrow glass.
Right. More molecules have access to the escape hatch.
Pretty much.
And this whole process hasn't always been the same throughout Earth's history, has it?
Not at all. On early Earth, with higher temperatures, evaporation would have been incredibly intense. During ice ages, much slower. And today, global warming is increasing temperatures, which generally speeds up evaporation.
Which means more water vapor in the atmosphere.
Exactly. More fuel for storms, potentially more intense rainfall when it does come down. It's a direct climate feedback.
Is evaporation just an Earth thing?
Nope. It happens elsewhere. Mars has evaporation, but its thin atmosphere means the vapor mostly escapes into space, no stable cycle. Titan, Saturn's moon, has lakes of liquid methane and ethane, and those evaporate too. It's basic physics.
Wow, methane rain. Okay, back on Earth, what are some things we miss about evaporation? You mentioned plants earlier.
Transpiration. It's huge. A massive amount of the water vapor in the atmosphere, especially over land, doesn't come from lakes or oceans, but from plants releasing water through tiny pores in their leaves. They're basically sweating.
So forests are like giant humidifiers.
In a way, yes. The Amazon rainforest, for example, generates a significant portion of its own rainfall through transpiration. It recycles water incredibly efficiently. Deforestation breaks that cycle.
And we just don't see most evaporation, do we? From soil, rivers.
Even our breath releases water vapor. It's happening constantly, invisibly, all around us. It's not just puddles disappearing.
It really is like the Earth breathing out. Quiet, steady, but absolutely essential. Every storm, every river starts with this silent escape.
Couldn't have said it better.
Okay, so the vapor rises. Next up, condensation. This is where the invisible becomes visible, right? Clouds.
Exactly. Condensation is the flip side of evaporation. Water vapor in the air cools down, loses energy, and changes back into tiny liquid water droplets, or, if it's cold enough, tiny ice crystals.
Like on a cold glass on a humid day, or fog on a mirror.
Perfect examples. Or dew on the grass. And, of course, clouds up in the sky.
So microscopically, the fast-moving vapor molecules slow down as the air cools.
They lose that kinetic energy.
Yeah.
And as they slow, those natural hydrogen bonds between water molecules can grab hold again, pulling them together into little clusters, which grow into droplets.
But you mentioned earlier, it's not quite that simple. They need something to form on.
Crucial point. Pure water vapor actually struggles to condense on its own. It needs a surface. In the atmosphere, these surfaces are tiny particles we call condensation nuclei.
Like what kind of particles?
Oh, all sorts of microscopic stuff. Dust, pollen, salt from ocean spray, smoke particles from fires or pollution, even tiny bits of bacteria sometimes.
So clouds aren't just water, they're water clinging to stuff.
Essentially, yes.
Yeah.
These nuclei are like little gathering points for the water vapor molecules. Without them, the air could become supersaturated, holding more vapor than it theoretically should without forming a cloud.
Huh. And that leads to the dew point, right? That's the temperature where condensation starts happening.
Exactly. It's the temperature at which a given parcel of air becomes saturated, meaning it can't hold any more water vapor at that temperature and pressure. Call the air down to its dew point, and the vapor has to start condensing out onto those available nuclei.
That's why you see your breath on a cold day. Your warm, moist breath hits the cold air, cools rapidly below its dew point, and poof, instant condensation.
Precisely. And it happens in various forms: clouds high up, fog if it happens near the ground, dew on surfaces that cool below the dew point overnight.
And frost.
Frost is when the dew point is below freezing. The water vapor turns directly into ice crystals on those cold surfaces. It's called deposition, actually gas straight to solid.
Okay, now here's something really cool you hinted at earlier. Condensation releases heat.
Yes, latent heat. Remember how evaporation absorbs heat to turn liquid into gas? Condensation does the opposite. When vapor turns back into liquid, it releases that stored heat energy back into the surrounding air.
And that's a big deal for weather.
It's the engine for big weather. That released latent heat warms the surrounding air, making it more buoyant, causing it to rise further, which can lead to more cooling, more condensation, more heat release. It's the fuel that powers thunderstorms and hurricanes. Without latent heat release, those powerful storms couldn't form or intensify.
Wow, so every cloud, every raindrop is associated with this energy release.
Every single one. It's a massive energy transfer mechanism in the atmosphere.
And condensation has shaped Earth history too, obviously, building the first clouds, the first rains.
Filling the oceans, yeah, and later forming the snow that built up the ice sheets during glacial periods.
Does it happen elsewhere, like the methane on Titan?
Absolutely. Venus has clouds of sulfuric acid formed by condensation. Titan has methane clouds. It's a universal process, just with different substances depending on the planet.
Even airplane contrails are just condensation, right?
Yep. The hot, moist exhaust from the engines provides water vapor and plenty of tiny particles, condensation nuclei, and boom, instant cloud streaks in the cold upper atmosphere.
Condensation really is transformation, making the invisible visible and releasing hidden energy. It's water showing itself again.
Beautifully put. It's the atmosphere revealing its hidden moisture and powering its most dramatic events.
Okay, the vapor has condensed into clouds. Now for the main event, precipitation, water returning to Earth.
The grand release, you could call it. When those cloud droplets or ice crystals get too heavy to stay suspended by air currents, they fall.
And it's not just rain. There's a whole process inside the cloud first, right? Those tiny droplets need to get bigger.
Much bigger. A typical cloud droplet is minuscule, maybe 1/100th the size of a raindrop. It would just evaporate before reaching the ground. So they need to grow.
How do they do that?
Two main ways, depending on cloud temperature. In warmer clouds, above freezing, it's mostly collision coalescence. Droplets drift around, bump into each other, and merge, coalesce, getting bigger and bigger until gravity wins.
Like tiny bumper cars sticking together.
Kind of, yeah. But in colder clouds, where you have a mix of supercooled water droplets, liquid below freezing, and ice crystals, something else happens. The Bergeron process.
Okay, what's that?
It turns out ice crystals are more attractive to water vapor than liquid droplets are, especially at those temperatures. So ice crystals grow rapidly by stealing vapor from the surrounding droplets. The droplets shrink and evaporate, feeding the crystals.
Wow, ruthless.
Bit. These growing ice crystals get heavy, fall as snowflakes. If they fall through air that's warm enough on the way down, they melt into raindrops.
So a lot of the rain we experience actually started as snow high up.
A significant amount, yes, especially outside the deep tropics.
And then there are all the different forms. We know rain and snow. What about sleet and hail?
Sleet is basically raindrops that freeze into little ice pellets before they hit the ground, usually because they fall through a layer of freezing air near the surface.
Okay, and hail, that seems way more violent.
Hail is formed in strong thunderstorms with powerful updrafts. Raindrops get swept up high into freezing parts of the cloud, freeze, start to fall, get coated with more water, get swept up again.
Building layers like an onion.
Exactly. They go through cycles, adding layers of ice until they're too heavy for even the strong updrafts to hold, and then they plummet to the ground. Can be incredibly damaging.
Yeah, definitely. And precipitation, like condensation, involves energy too.
It does. Falling rain or snow carries energy downwards. And the processes within storms, melting, freezing, evaporation of falling rain, all involve energy exchanges that influence the storm's structure and winds.
It's all connected. And precipitation patterns tell a story over time, don't they?
Oh, massively. Those first epic rains filling the oceans, the shift to snow during ice ages locking water away, the intense tropical downpours versus the rare desert cloud bursts that reshape the land, mountains catching snow and rain, acting like natural reservoirs feeding rivers.
And humans are deeply affected. Agriculture is totally dependent on it.
Entire civilizations rise and fall based on rainfall patterns. It shapes culture, mythology rain as cleansing, life-giving, sometimes sorrowful.
And we even try to influence it with cloud seeding and stuff.
We try, yeah. Results are mixed, controversial sometimes. But it shows how critical precipitation is. And in cities, heavy rain on hard surfaces causes huge problems runoff, flooding, pollution.
And climate change is messing with these patterns now, right?
That's one of the clearest signals. Warmer air holds more moisture, so when it does rain, it can rain harder, leading to more intense downpours and flooding in some places. But that same warming can worsen droughts in other areas. Precipitation is shifting, becoming more extreme in many cases.
It really is the cycle's climax. Gentle or violent, it's water returning, completing that part of the journey.
The moment the invisible becomes tangible again, shaping everything on the surface.
Okay, the water has fallen. Now, collection. This sounds simple, water gathers, but you're saying it's more complex.
Way more complex than just flowing into a lake or ocean. Collection is really where the water arrives at a crossroads, taking many different paths, some fast, some incredibly slow.
So what are the main paths?
Well, some becomes surface runoff. It flows over the land surface, maybe into a street gutter, then a stream, a river, and eventually the ocean. That's a relatively fast loop back into the main cycle.
Okay, runoff. What else?
A lot of it infiltrates the ground, seeps into the soil. Some of that soil moisture gets taken up by plant roots, goes up through the plant, and is released back to the atmosphere as vapor. That's transpiration again, a quick local loop.
Right, the plant's sweating.
But deeper infiltration goes down further, recharging groundwater and aquifers. These are vast underground stores of water, and water can stay down there for a very, very long time. Decades, centuries, even millennia in some deep fossil aquifers.
Wow, a hidden slow motion part of the cycle.
Hugely important. And then, of course, in cold places, precipitation collects as snowpack and glaciers. That's water locked up as ice, another form of long-term storage, releasing slowly as it melts, often feeding rivers in the spring and summer.
So runoff, infiltration to soil and plants, groundwater and ice. And eventually a lot ends up in the oceans.
The oceans are the ultimate collector, yeah, holding about 97% of all Earth's water. And even there, the water isn't static. It circulates in currents, some near the surface, some in the deep ocean conveyor belt that can take 1,000 years to complete a circuit.
So collection isn't one step, it's like a whole branching network of subcycles.
Exactly. You've got fast loops, slow loops, surface loops, underground loops, frozen loops, even human-made loops with reservoirs and water treatment. It's incredibly intricate.
And messing with these collection pathways has consequences, like pumping too much groundwater.
Big consequences. Overpumping aquifers drains those hidden reservoirs faster than they refill, causing wells to dry up, land to subside. It disrupts that slow, natural balance.
And melting glaciers.
Same idea. Glaciers and snowpack act like natural timed-release water towers. They store winter precipitation and release it slowly during warmer, drier months. Faster melting due to climate change means too much water, too soon flooding perhaps, and then less water later when it's needed most. It disrupts the rhythm.
Even soil moisture matters hugely.
Critically, soil holds water for plants. Plants keep ecosystems going and contribute to rainfall via transpiration. Degrade the soil, lose that storage capacity, and you impact everything up the chain.
So collection, these storage phases, they're like the regulators, the buffers.
Perfectly put. They regulate the flow. Without storage in soil, groundwater, ice, lakes, reservoirs, Water would just flash flood straight to the sea after every rainfall, leaving landscapes barren most of the time. Storage creates stability, allows for sustained life for agriculture, for us.
It makes you realize the cycle has memory. Some water remembers yesterday's rain, some remembers the last ice age.
That's a great way to think about it. Collection is where the cycle pauses, stores, remembers, before moving on. It's the hidden rhythm section, keeping the whole system in balance.
So wrapping this all up, it's so clear that simple school diagram barely scratches the surface.
It's a starting point, but yeah, the reality is this vast, interconnected web. Loops within loops. Fast, slow, visible, hidden.
From cosmic dust delivering water billions of years ago,
To the latent heat in a single cloud fueling a hurricane.
to plants breathing out moisture driving rainfall.
To water locked in glaciers for millennia, or flowing in unseen rivers underground.
And now, unfortunately, pollutants hitching a ride through the whole system too.
Yeah, that's a crucial, sobering point. The cycle carries pesticides, plastics, chemicals globally now. It's not pristine.
But through it all, the core pattern remains, doesn't it? This constant movement, storage, release, renewal.
It's fundamental, not just to water, but maybe a pattern for life itself. Constant change, transformation, return.
Makes you appreciate every single drop, knowing the journey it's been on and the journey still ahead.
Absolutely. It connects us all through time and space.
So maybe the next time you feel the rain or see a cloud or pour a glass of water, just take a second. Think about that journey. And maybe think about other cycles in life, big or small, that echo that pattern of movement, storage, release, renewal. How are we all part of these flows?
A deep thought to end on.
Thanks for diving deep with us today.